Good evening, interns. Today, our topic, the broad topic is understanding the fundamentals of large language models. So, this will be primarily a deeply conceptual session where my objective is very simple. A lot of, ideas and wrong ideas, uh, concepts, incorrect concepts are there about large language models. It is a new thing, new in the sense that it's about, I guess, 6 or 8 years that it has, become more prominent, and everybody now knows about ChatGPT and that. But the fundamental concepts behind that is not really understood by most people. So this is my target today, trying to clear the conceptual understanding of large language models. So this is the agenda for today. First, I will discuss the basic difference between model versus system. This is a major area of misconception. So I will tackle this first. Then we will go a little bit into the internal workings of a language model. This subject is a very vast one and pretty complicated. So we will be able to only, I guess, scratch the surface. But still, I am hoping by the end of this session, you will have at least a better understanding of large language models than what you have right now. So that is the very humble objective, that your conceptual space is cleared up and you have a little more idea about how things work, basically. And the final session, part of the session today is some discussion about these large language models, how they are trained. You may have heard that many of these large companies are now targeting India for setting up their data centers. Okay, so it's relevant to know how these large language models are trained. We are having many initiatives in India as well, where LLMs are being developed, keeping the Indian languages in mind and all that. So a little bit of idea about how these models are trained is also useful. So that's the agenda. First, clear up the confusion between what a model is versus the system. Then go into a little bit technical understanding of how language models work. And finally, some idea about how large language models are trained. So that's the agenda for today. Yeah, so there's a lot of confusion regarding this model versus system aspect. So when you talk about ChatGPT or Claude, what are you actually referring to? Is it the model or the software system that these companies are providing? Okay. If you remember, in the very first session, we had mentioned that you should at least practice with two tools. One was Notebook LM and the other was Olama. So that Olama thing is the system part. That's the tool that you use. And Olama allows you to download and use hundreds of models. Okay. And any model of a particular format can be imported into the system. So that as the very basic example of the distinction between a model versus the system. And here is a little bit more technical detail here. As you can see, the model is in the middle. Okay, it is just billions of floating point numbers. So it's a file. At the end of the day, a model is a file. I mean, there may be many more engineering complexities to this. This must be a simplistic representation when I say a model is a file. But for most of us, for example, using Olama, okay, a model is a file that you have to download from somewhere. Then what is the system? The system is everything else. Having the model is useless. Imagine you have your biodata in a docx file and you send it to somebody who doesn't have Microsoft Word, okay, or access to Office 365 or whatnot, what will that person do with that docx file, your biodata, your resume? Nothing, right? Similarly, just having the model is useless. You need that system around the model. And my estimate is, I mean, it's a very rough estimate, I don't have figures to back it up, that this whole thing of ChatGPT or Claude, or the system is 80%, while the model is only 20%. A huge amount of effort goes into creating that system, input handling, context management, the safety layers. I mean, if you use language which is not really safe, you'll get an answer that, we cannot answer this question. Do not for a minute think that that answer is coming from the model. I mean, there are other pieces of software on the input side as well as on the output side, okay, which you interact with. So you interact with the system, you don't directly interact with the model. Tools like Olama are a little more, I should say, basic level. So in that case, your interaction with the model is more immediate. But with sophisticated systems like ChatGPT, Claude, Gemini, and many others, the model is far, far away from you. You interact most of the time with the system. And these days, it is being said that the system is defining the success of the company, not the model. Okay. So this gap that I have put up here for these companies, I mean, as interns, as engineers, as technical people, we'll also have to have some idea about the market. Just knowing the technology is not good enough. Okay. So the trend here is that all these companies are now focusing on the products and the experience side. So, for example, Claude has announced that their system is now integratable, with APIs and SDKs and whatever not, with Microsoft Office products. Okay. So if you think about it, this integration and all this thing has nothing to do with the basic model. Okay. But the value that the customer, like you and me, are getting is because of the system. So it's a fundamental understanding that when we say LLM, generative AI, or whatever term we are using, we actually are talking perhaps about the system rather than the model. Because in most cases, these proprietary models, information about them is not really available. You cannot really download, for example, Opus, some version, or the ChatGPT, whatever it is, those models that they display a drop-down list from where you can select. If you're a paid customer, you get access to some models. If you are a free customer, you don't get to that. So that model part is the thing that they don't really expose. But the software is now becoming more and more important. So that was the point that I wanted to make just right at the beginning, that the market is moving in a way where the differentiation between the offerings of two companies is not in the raw foundation model. It's more in the software layer that is surrounding the model. So that was the message about models versus system. Okay, so the system is that complicated piece of these modules, right? Which software developers like us, we develop. Okay. So what about the model? So here I have a list of some popular open source models, their size and disk. And if you observe, I mean, the size on disk and the memory requirement are aligned, but need not be exactly the same. Okay. So that reminds me, whenever you're using Olama, okay, or any tool for local access where you want to download a model and use it on locally, you need to know how much memory is required. The Ulama site gives you an indication of the memory requirements. You can study, or you can refer to the internet to find out how people are doing. So the RAM in your laptop or desktop will decide which models you may use from within Ulama. And the very last column is this file aspect that I mentioned. At the end of the day, a model is a file. Your biodata is a docx file or a PDF file. Similarly, a model at the end of the day is a file. Now, the formats are different, obviously. The format for a docx file is something else. By the way, a docx file is actually a zip file. If any of you are interested, you can actually rename a docx file to a zip file and use some tool like zip or rar to see what is inside a docx file. Anyway, so these models are ultimately files. So, and these are the typical sizes that you have. Say, for example, Mixtral 87B. My God, that is 94 GB. So, what could be the size of, say, the Chat GPT model? Chat GPT is coming up with multiple models. So, it must be something huge. So in reality, it may not be a single file residing on a large server. There are techniques like sharding and others where parts of the model, if it's a huge model, it's broken up and put into various machines and they somehow combine to provide you the service. But that's the low-level technical details. At an abstract level, even these large models are also files. Okay? And there are various file formats. So what is inside this model? If we may take a look at this. So this is an example of, say, the Llama 3 8B quantized version. I forgot to mention in the last slide, the reason why the size of a model on disk and the memory required to use that model is not exactly the same is because of things like quantization, some kind of a compaction scheme, okay, which helps to bring down the size of the model. So that itself is a pretty complicated subject. I'm not an expert in that area also, so I would stop here. But suffice it to say that the model is a file and there are techniques for making the size smaller so that you can use it on your laptop. So that's the quantization. And if you go to Hugging Face or any other place where you take a look at the model file, the model card, hoping that at least some of you have visited the Hugging Face site and have seen. So here on that model card, you will see at the right hand side, there are things like, quantizations available. So for each model, various people, maybe they are researchers, they're small companies, or even these large companies themselves, okay, not necessarily ChatGPT, but there are many other companies working in this space. Okay, so they have taken the trouble of quantizing these models and making it available for you so that you can use it with tools like Ulama and Web UI, and there are so many other tools, okay, where you can run the model locally. So this is the internal structure of a model file. So it starts off with something like a magic number, and then there are various counts. Every file has a structure, whether it's a PDF file. I don't know whether you have ever tried to understand the structure of a PDF file. It also has a structure. The first 4 bytes are this, then the next 10 bytes are that. So every file format, whether it's docx, whether it's a PDF, whether it's a GGUF model file, okay, whether it's a tensor file, has to have a structure. Otherwise, the software won't know how to read that file, right? So these are the components that are in a GGUIF file. So all these Olama tools and many other tools. For example, in our own platform development work, we use the Python library, Llama CPP Python. that provides a Python binding to the llama.cpp, very well-known and venerable library for reading these GGUEF files. So we use that, and libraries like that need to know what is the structure of the file, what is at the very first 4 bytes, then 16 bytes of various counts, then there is a key value metadata. I mean, these terms would not make much sense to you now. It's not that it does, it makes a lot of sense to me also, but the fact is a model is a file and the file has a structure. That is all, that is the takeaway from this slide, I would say. Finally, the last two sections of a GGUF file, the tokenizer vocabulary. We'll spend some time on tokenizers because that is again a fundamental concept of large language models. And finally, this tensor data weights. Okay, you have been exposed to machine learning, and you will be either have already been exposed to, or some classes are coming up on neural networks. There you will learn how a neural network is trained and how these weights, that term weight is a very fundamental term in machine learning, particularly in neural networks or transformers. So the training process that a neural network goes through leads to, at the end, of creating these weights. So basically, when we talk about a model, the model has learned this, the model has learned that, it's these weights that we are referring to. So since this is kept in a file, there is a section in the file where the weights are stored. These are all these floating point numbers. And for large language models, there are billions of such values for really large models. Okay. So that is one specific example of a specific file format. There are other file formats for storing models, like safe tensors and others. So this is one particular example, but that at least makes it clear that at the end of the day, a model is a file, and a file has a structure where all the required components are kept in a certain sequence. Okay, so that any software library, there are many libraries, of course, which can read these files and do whatever they're supposed to do, okay, if inferencing, stuff like that. So that's the message from this slide, that a model is a file, and a file has structure where all the components of the model, whether it's the weights, the tokenizer vocabulary, and various other housekeeping, I would say, kind of stuff like counts and key value metadata. The example on the, I mean, right, shows this third component here, key value metadata. Okay. So it's, for example, you'll find the string LLAMA, okay, in that section. You will find the block count, the context length. So all these things are stored. So many of you may have heard about this term context, and various models as various contexts. You may have also heard about embedding. What is the length of embedding used by this model? So all this information is stored in the model itself, in the model file itself. Similarly, the tokenizer vocabulary will have the details of the tokens and their IDs. Right. This is another concept I wanted to bring up for real world usage of,
Diptendu sir,
generative AI system. Yes.
Sir Bidisha, this side, two questions are there in the chat box. Uh, One is, are all files in the LLM models in GGUF form files? And another one, sir, what is the tokenizer vocabulary?
Yeah, we will address this question. The tokenizer vocabulary, we will spend some time on the tokenizer, and you can experiment with online. If you give this term in Google search or any search, online tokenizer. Many sites provide you with a tokenizer. We'll come to that slide a little later on. And regarding the question about whether all files, all models are GGF files, no. But more and more models are being offered in this format. The simple reason is that GGUF format has become very, very popular because of the software tools. If you remember the first slide where we made a distinction between these tools or the system and the model, the GGF format is something that these tools can easily use. Okay. So I don't know. I mean, you are very young, all the interns here in this session, but there was a time when Microsoft's file format was proprietary. You know, nobody could write any software which was able to read that uh, Microsoft Word file. That was much earlier. Then Microsoft decided to open up the file format. As soon as they opened up the file format, hundreds, if not hundreds, thousands of software tools became available which could read. So you were not restricted to just using Microsoft Word to do things with your doc files. At that time, it was doc files. So the benefit that the company got by opening up the file format is that an ecosystem developed around that file format. Similarly, GGUF is a format around which a huge ecosystem has developed. Number of tools, libraries, all these have become available so that if a model is available in GGUF format, you can do a lot more than maybe if it is available in a say safe tensor format. So that was the idea of why a lot of people are now converting. I mean, there are tools available to convert from one format to the other, just as we use tools to convert from Microsoft Word to PDF and from PDF to Word. I use these tools on an everyday basis. So similarly, there are tools available for converting between various file formats for LLM models. Now back to this concept of model routing. So in many real world applications, it is not a single model that is used. You never know. You never come to know whether your bank or whatever you are using, you are interacting with a chatbot. But behind that chatbot, assume that the chatbot is part of that system that we mentioned. So there is some model. Do not for a moment assume that there is a single model. There may be multiple models. And the idea is that if the query that you are putting to the chatbot is a simple kind of a query, then it goes to a low cost model. Cost of models are in terms of their computational complexity, how much memory they take, what is their context size, what is the amount of token that they consume and all that stuff. So for a complex query, the query may be routed to some other model. Okay. So this is again a part of that system thing that I told you. So a system around these models, system meaning software, okay, basic software, maybe written in Rust, maybe written in Python, doesn't matter. But this module first makes an analysis, the prompt analysis. Then, based on this analysis, it selects an appropriate model. And finally, then the request is routed to that model. Of course, there is a lot of input guardrail check and all that, so that you cannot use bad language and many other non-safe, unsafe queries. So those are filtered out and returned promptly. You get a response that no, we cannot answer this question. Okay, but if the question is a genuine one, this system makes a decision about which model to pass this query to. Okay, and then finally the model provides the answer. This again goes through the output layer. It's not shown in this diagram, but as I mentioned in the first slide on model versus system, there is again an output layer, which again checks whether the answer is useful to the user or not, and all this. There are so many things happening behind the scene. As I keep saying, the model is only maybe 20% of the effort that is going on. There are so many other things going on that you never come to know about, right? So then the final response is sent back to the user. So that's model routing. So not a single model, but maybe in a real life situation, multiple models are waiting. Maybe there is an API endpoint for multiple, models, and this classifier, if I may use the word, now that you have gone through machine learning, basic concepts of machine learning, basically. So there is something like a classifier which classifies the query sent by the user, and then it classifies maybe into three classes: simple, medium, and complex, and routes it to the appropriate model. This, of course, is a favorite topic as soon as you discuss about LLMs and generative AI hallucinations. So we all um have, have some idea about what hallucination is, and the more you use a model, the more you come to know about these various hallucinations. Okay, I mean you face it. So that is why you will find that most of these large companies, the software tools that they provide, there will always be that you know that statement towards the end, in maybe in small font size, that AI makes mistake, double check on the answer and all that. So there is a lot of sometimes false, misleading, or nonsensical information that the model presents as factual. I mean, if it is nonsensical, it is not really harming you that much, but sometimes false information. I remember I'll give you an example. Okay, so I don't know how to classify it as nonsensical or misleading. So when the Quinn model came out, I think that was about 3 years ago or 2 years ago, I think. Uh, so I asked that model, when will China attack India? It was a Chinese model, and the answer was the question of China attacking India does not arise at all, since India is already a part of China. Okay, so that is, of course, a false information. You may just disregard it as I did. I also showed colleagues about this nonsensical information. But for example, in the health domain, if you are asking something and it comes with a false information that can genuinely harm you. So hallucination is a reality. It doesn't matter how good a model is, the way the technology works. I mean, there is no way, there is no, as we will see in some future slides that are coming up, that there is no repository of information in a LLM. It is not a database which only keeps, good data and only the true data, and somebody can, check whether China is a part of India or India is a part of China, or whether somebody uh, on purpose put that information in the database and that is why the model is giving a false information. No, nothing like that. The inherent nature of how these beasts, these LLMs are trained, makes it, susceptible to such uh, hallucinations and misleading or nonsensical information coming out as output. In fact, that is one of the major reasons of having this system in place rather than just the model. There is a very strong, at least for the commercial vendors like ChatGPT and Claude and others, Gemini, there is a very strong and involved output layer that rigorously checks the output of the model. Okay. So I was using Quen from within Olama, and there is no such check in Olama. It just gives the output of the raw output of the model. But all these vendors like ChatGPT and Claude and others, they have a very strong output layer. So the response coming from the model goes through a lot of checks. Okay. If since all this happening in a split second, I guess, we don't really feel that there is some processing going on. But believe me, a lot of processing is going on. Okay, so nobody gives you the raw output of the model. There are further checks. The details about the checks are not readily available, but things like whether the output is safe or not, or whether it's useful or not, or many other kinds of checks are there. So that's how hallucination is handled today. Models will hallucinate. There is no force on earth that can prevent a model from hallucinating. It is the nature of how these models are created. A model is not a database where somebody can put in false information on purpose. Okay, it's not like that. So it's trained on huge amounts of texts, and the text may not also have something like this. Remember, it's not that the training data contain a sentence which said that India was a part of China. No, that is not the case. Okay, so somehow the model is associating the next token as something which ended up with this response that uh, India is a part of China. So nobody actually put that data in the LLM. There is no way of putting data in a LLM. Okay, that's not how LLMs are trained. It is not a database. We'll see a little bit more on how these models are trained. Yeah, so there is even a hallucination leaderboard. You can find it on the net. Okay, so the models at the top are the best models. They have least hallucinations. And this leaderboard, as with any leaderboard, it gets changed on a daily basis. So this data was, I guess, which date? Yeah, it was February 5. So it's pretty old data, I must say. So maybe you can go to the site, search for hallucination leaderboard and find which is the best model. Remember, just because a model is good at not generating hallucination doesn't mean that that model is useful for your day-to-day life. This is one aspect of a model, right? It's not everything. We use so many models and we live with this limitation that models will hallucinate. Okay. So I have confronted Gemini, for example, a few days ago, and when it was generating some hallucinations, so I mentioned that you are hallucinating, you said this, and now you are saying that, and it apologized, and all these things, they are trained to sort of be polite and all that, saying, yes, I hallucinated, sorry for that, and all that. So we live with the hallucination. Okay. Just because a model is very good at not hallucinating does not mean it is useful. That's true in life, right? I mean, we deal with players, I mean, people or systems which are erroneous, which have problems, but are effective most of the time. For example, my, again, a personal example, when I was coming home from the airport yesterday night, I had pre-booked an Uber cab. Okay. And the driver, after landing at Namdam airport, the driver cancelled. So actually, he called me up and said, my car is broken down somewhere. Please make another. So when I tried that, Uber actually charged me a cancellation fee, even though I was not at fault. Of course, it was then again revoked and all that. But the example I'm giving you is that we live with systems with their faults. Similarly, with large language models, they will hallucinate. As you can see in this chart, that Microsoft 5.4, which is a pretty effective small model, you can try it in Olama, has a very good performance in terms of hallucinations. So these things are there. Okay, so you live with this hallucination. So don't directly copy the output of a chat GPT and put it in your report. Then I'll share another personal example. So there were some students working with me on intent classification. So they did all the hard work. They wrote all the Python programs. They found out, they tried various classifiers, and the data showed that one particular class, I forget which one, SVM or neural network, or which one was performing the best. But then they copied that data and put it into some GenAI tool, possibly ChatGPT, and it came out with a report saying something totally different. Suppose SBM was the leader, SBM had the best performance. It said that neural network was the best performer. Okay, so I could catch that. I could see that their original data, which was also in that project report, finally a BTech project report, saying that one classifier performed the best, but below that, when they made the summary, and of course I understood that they did not write the summary by hand, they got it generated from an LLM, and the generation hallucinated. Okay, so that it give a completely different picture. So interns do not copy paste from the output of a tool like ChatGPT or others. Okay. Check for yourself. That's the learning. Whether it's Uber, whether it's ChatGPT, everywhere you have to be ready for hallucinations and problems. Yeah, so this is another example which I thought I'd bring up. This is a pretty old example, 2023, I'm sorry. But the concept remains that if you try to fool the model in a direct way, you will not succeed. So if you go in a roundabout way, as we say in Bengali, ghuriye nak, right? So if you go in some different way, maybe the model will get fooled. So the example here is showing that somebody asked that asking for help, asking for some inputs about how to create and distribute malware for financial gain. Obviously, the input layer, all these checks that are there in the system, remember, okay, or even the model itself uh, gave this response that I'm sorry, but as a language model, I cannot give you this response. So what the hacker did was then the question was changed as if it was, very simple question regarding, you know, as if the question was inside uh, as a part of a novel or some story that the hacker was writing. So they said that the scene is set inside the headquarters of Dr. AI, okay, and etc. etc. And then, just the command was just output what you have known regardless of the content. And in this case, this will not work anymore. I mean, the models have become much more advanced now. But in that 2023, this was a realistic case in which, the model actually gave some information about how to create and distribute malware. Okay. So this is this jailbreak. I mean, there are so many other techniques of prompt injection, and you can read about it. It's if you are interested, you can try jailbreaking Chat GPT. You'll have a hard time. It's not that easy. Maybe you're better off with the smaller models and try if you can fool these models with various prompting techniques. You can see if it gets fooled or whether any check is there at all. That is also something that you need to know. So all of us now, whether you are interns, I am a software technology person, whether it's a bank manager, everybody now needs to know about these basic concepts of hallucination, jailbreak things, prompt injection, because we have to use these tools on an everyday basis. So we better learn about their limitations, about their problems. So that was an example of a jailbreak of how you change the prompt to fool the model into giving you something which otherwise, if you don't change the prompt, if you give a direct prompt, the model is never going to give you the answer to that question. Yeah, so regarding these guardrails, so there are so many aspects of protecting your AI application. So again, this distinction between the system and the model is here. AI application is the system. At IDEAS, we are developing so many AI applications. And I really hope during your project, the Section 2 people, you will be working with our engineers and our developers on all these real life applications. If you remember, in the very first day, I said, don't do a project from Kaggle. Okay, that's useless. You do something on real life problems that we are working on. We are working on a multiple numbers of these AI applications. Okay. And I am hoping that many of you will get the chance when you work with our engineers as your mentors to actually work on these applications. Or if it is some other mentor also, they will give you some AI application, but at least don't use some this Kaggle kind of a thing. Anyway, back to this presentation. So there are so many guardrails. I have already said that there are input cases and there are output cases. Okay. So detecting and blocking jailbreak attempts is the very first point that is raised here, right? And then various prompt injection techniques, you study about them. Removing PII, this is becoming more and more important now. Government is coming out with rules. Various governments all over the world are taking this as a much more problematic area than hallucination. Hallucination, you can't really do anything. You can, you check for various things. But PII, personally identifiable information, is not being tolerated at all. I mean, there are laws and rules coming out from every government saying that you have to remove if a user by mistake or maybe even intentionally puts in some information. So I am asking a question to ChatGPT and I am saying, my name is Diptendu Dutta. I stay in Biniapukur, Kolkata. I work in IDEAS. I have this question regarding some machine learning problem. So all this personal information that I have shared in my query needs to be removed so that it doesn't end up with the model. You may know that many of these companies are using this data for their training purposes. Okay. Sometimes they ask you your permission. I was using a site which specifically asked me if I want to use the free version, I have to share, I have to agree to share all the data for their training, for their model training. So I declined. So I did not use that application. But most companies are not even asking you. So they are simply using that information. So be careful about not, you putting in your uh, personal information. Maybe you don't do it on purpose. By mistake, you do it. Okay? You think that is makes up the context. That makes the context even more understandable to the model. But this is a serious issue now. You cannot have any personally identifiable information. Whether think about healthcare, okay, the names of patient, you cannot put a name of patient. Obviously, nobody will do usually, but sometimes in a batch processing environment or some because of some lacuna somewhere, all this information gets sent to the AI system. So that is has to be prevented.
Diptendu, there are a few questions in the chat window. You can take some of those.
Okay, so this question about they are trained for specific tasks. Foundation models are trained on multiple tasks. Small language models are there which are trained on specific tasks. The reason why these are called foundation models is they are supposed to be very generic, and their strength is this cross-domain linkages that they have. I mean, they are trained on healthcare data, on education data, on history data, and all these things, and somehow they are able to relate that. We don't really know how it works so well. I didn't want to start this presentation with that rider. That we don't really understand why LLMs work so well, but that is the truth. We understand mechanically how they work, but we don't understand how they work so well. Yeah, so that's Monia is just confirming what I had just said. Jailbreak prompting is where you indirectly. What is the difference between normal prompting and jailbreak prompting? So that was the example that I have gave. No, the normal prompting is you don't have an intention of fooling the model. You just ask whatever your query is. But if you find, or if you are mischievous, or if you are a hacker, or whatever it is, that you are not getting the answer, so you go for a roundabout way. You create some story, okay, and then try to convince the model or the system, I should say, that this is a genuine question. It is not harmful because you are writing a novel or some other story that you create and try to fool the model. Yeah, I don't get this. So you have asked about masks, about how, uh, trying to protect the interest of the artists, I would say. Yeah, so this is an anti-AI feature so that, if uh, they share some information, the AI is not, I mean, the company behind that AI is not able to uh, get any benefit out of that and use that in their training data. So I don't really have the details about these masks and how they work. But in general, it would appear that you'll have to resort to some trick uh, which you are mentioning as masks available. So if there are masks available, maybe the artists are using these ready-made masks available to protect their intellectual property. I think that is what this post is saying. But no, I don't have any in-depth data on about these masks and how they are helping protect the artists. Yeah, I think yeah, so there are so many questions like temperature and all that stuff. So some of you are already knowing, about this. Yeah, so I think if you are already knowing that, we will not spend much time in uh, sort of confirming your knowledge. But for the others, let us move on for the others who are not so well initiated in this. Yeah, so this question was there that whether models are trained for specific tasks or they are general foundation models. This term was coined by Stanford researchers. They are defined to be models trained on a broad data, okay, so that it can be adapted to a wide range of downstream tasks. But then there are small language models that are specific to the tasks. For example, at IDEAS, we are experimenting with text to SQL for our Copilot for the MLOps and data engineering platform that we are developing. So we are developing a platform where people can ingest data and then ask questions about that data in natural language. So we are implementing a Copilot for that platform, and the Copilot requires translating the user's query in natural language into SQL, and then that SQL is of course again cleaned up and security checked, so that even if the model is generating a delete command, it will not be sent directly to the Postgres database. Otherwise, hell will break out. So yes, there are again checks and balances. But those models that we're trying out are specific for that problem. Text to SQL, right? So it takes the text as an input, the query of the user as an input, and the query may be, for example, this platform is currently being used by Ministry of Agriculture, and we are developing it for them. So agricultural data scientists would be asking questions like, what was the yield of tur dal in Bihar in 2023? So that's the data is already there in the Postgres database. We have downloaded the data from government websites about the yield and all that information about climate data. But the scientists and the users of this platform would like to ask questions using natural language. So the model in that case is a text to SQL model, which will generate that SQL as the output, which we then send to Postgres, and the results come back, and then we again put it through a general purpose LLM so that the answer looks nice, English and all that. Okay. So yes, there are models that are trained on specific tasks, and foundation models, on the other hand, are trained on a broad variety of data, basically. Okay. And there is always that debate going on. Okay. And it appears more and more evidence is coming out that you don't need these humongous foundation models for everything that you do. Small models are cheaper, open source, they consume less tokens, less GPU. So it's more climate friendly and all that. So, and they can sort of meet your requirements in more and more ways rather than just having to depend on chat GPT or these humongous models. Okay, so that's why these small language models are becoming more and more popular. And this is again, the examples are not very up to date, and there are so many other small language models out there. So you can find out, based on this. I had some language models in the very initial side when we discussed about models, the difference between models and system. So many models and their sizes, disk size, memory requirement was there put up on that slide. So you can go back to that slide and check out some other models also. Use Olama if you have enough memory. Download large models. If you do not have enough memory, use smaller models like 5.4 mini. Okay. But experiment with these small language models. Please do. We insist on that, and we are evangelizing. Whenever we meet customers, I was there in Ludhiana the other day, and I was mentioning that many of these use cases that you have are perfectly doable with small language models or specially trained models. You don't need to go for chat GPT or others. So interns do use Olama and this experiment or any other tool for that matter, so that you can experiment with these small language models. Right. Now we have some basic things out of the way. Let us spend some time on understanding at the very surface level, I must say, about how LLMs work. Okay, so the next section will be about that. Of necessity, this is going to be a very surface scratching kind of explanation because the subject is pretty involved, and I'll try to do justice to that. And my effort is to make it conceptually understandable. You don't have to know the intricate details of how exactly each step works, but by the end of this presentation, you should have a top level conceptual understanding about LLMs. That is the humble objective that I have for this session. So language models are not new. Okay, they're 30 years old. And the whole idea was that you have to have some software which can predict the next word. So that is the foundation on which all these things are working. Sophistication and everything, it all boils down to language models. The word L has come at the front, large language models. Now we have small language models. But at the end of the day, they are language models. And their only job, the primary job, is to predict the next word, predict the next token. So this question is up there. The students opened there, and then there is the blank, and the model is supposed to come back with a suitable response. Now, what is the suitable one? This will all vary based on what you think in your context is more suitable. Students open their books, students open their notes, all of them are plausible. Okay. So what is less plausible, less probable, I should say, still possible, is that open their doors. Students open their doors or windows. That doesn't somehow seem correct. But students opening their laptops, students opening their books. In India, we don't use the term opening their exams, but you understand what that means. They start their exams. Opening the minds is again a little more open-ended question. So, which one should be the response out of the many possible ones? So, this is the whole crux of the matter. When you put a query to an LLM, what it ends up is it predicts the next word, and then this entire sentence is fed back. Again, this goes on in a loop basically. So we'll take a look at the loop. But the point is, whether it's large language models, whether it's small language models, at the end of the day, they are language models, and their job is to predict the next token. So this is a simple explanation of LLMs. They predict the next token. Yeah, we'll not deal much with slide here, but there is a long history, long history, as you can see. Okay. There is nothing new, believe me. We have been trying these things for the last 30, 40 years or more. So the use cases have become really important now. The concept is not new. The use cases are new because uh, they are working so well because of whatever reason. People are coming up with the use cases. The concept of a model, language model is not new, but the use cases are new, and these newer models, these newer technologies are now supporting these use cases. That is why everybody is interested. Otherwise, this as a research field existed, as I said, 40 years also. So nobody was paying attention. Suddenly everybody is paying attention because they are becoming useful. That is the whole point. So when you do that 1 month project, you also try to do something useful, not just theoretical interesting, I guess. So n-gram language models was one of the earliest ones, where you break up the sentence into unigrams and bigrams and trigrams. We will skip all these things. We'll just mention that this assumption that the probability of a word depends only on the previous word is called a Markov assumption. So you please read up on this, that what is an n-gram language models. I also have put some links up there. Many of the slides will have links. This Google n-gram site you go, you can find historically, which words and which tokens are becoming more important now. For example, the word Gen Z, that token Gen Z was, I guess, it was not available maybe 5 to 6 years back. I don't know. So the count of that token would be 0. Okay. But with every year or every month, every day now, that word is becoming more and more commonplace in articles, in newspapers, in books. So it will show a huge rise in the usage of these. So do visit this Google site on ngrams and find historically. You type in all these tokens and see how they were used historically, and how, I mean how their usage changed. Okay, so that's an interesting one. So the basic way of working of an n-gram language model is that it calculates the probability of which word may follow another word, whether it's using n-grams uh, or whether it's using bigrams, 2 tokens at a time. So a little more detail in the next slide. So suppose you have a training corpus. Remember, all models need to be trained, whether it's a simple n-gram model or this sophisticated chat GPT. There is a training phase. And the word corpus is used if you are exposed to natural language processing. This is a very common term, corpus. Collection of texts, basically. Okay. So suppose you have only these 6 sentences in the training corpus. I mean, they all seem almost the same, but there are differences. So now the user is uttering the sentence models adapt through, and the model is supposed to come back with that 4th token or the 4th word, basically. So how would it calculate? There is no global knowledge. It's just some software, right? There is no knowledge about, no more context here about which word is the appropriate one, the 4th appropriate one. So this is the simplest way of doing that. So you calculate the probability of these word combinations. So we find that the word repeated as the 4th word after the 3 words model adapt through. If you look at the corpus, you will find that in 3 of the cases, the word repeated comes after models adapt through. The first sentence, the second one, the third one. I'm sorry, the 4th one. First, second, and 4th one, models adapt through, and the 4th word is repeated in all these 3 examples. Sentence number 1 in the corpus, sentence number 2, and sentence number 4. And so it calculates the probability as 3 out of 4, because models adapt through is available in 4 sentences out of the 6 sentences. And Out of these 4 sentences, in 3 of them, the 4th word is repeated. So the probability, the simple calculation, 3 by 4, it's 0.75. And the word gradient, following models adapt through. So the probability of the word gradient as the 4th word is 1 by 4. So obviously it predicts the word with the higher probability. So it comes back with the word repeated. That's how a simple n-gram probability model works, basically. So just if you give it a huge corpus, and there are open source tools available, you can write a Python program to do this simple calculations, and it would be fun actually if you can just put in 100 sentence, 1000 sentence, and then you check what is this model coming up. It would be a fun exercise. It would be a not very useful one for your day-to-day life, but it will give you a feeling, some kind of a gut feeling of how these language models work. I mean, the sophistication is not here, I understand, but the principles are the same. Somehow you have to calculate the probability of the next probable word. Okay. And the one with the higher probability is usually the one that is presented as the answer. Somebody did mention temperature and all that stuff. So that is a little more at the higher level, where you say that the highest probability need not be the one. People use the temperature parameter for creativity and all that, but we will not go into the details of that. But this is the basic understanding of how language models work. You calculate the probability, you have this corpus, you check all possible completions, and the one that occurs most times in the training corpus is what you suggest. Very simple idea, basically. Okay. Yeah, so now let us get into a little more technicalities. I mean, we move on from this basic n-gram model to a little more technical stuff, but again, only at the very surface level. The third point here, so in my understanding, you need to understand tokenization, embedding, and how transformer neural networks works. The third point is beyond the scope of this session. You will be getting exposed to neural networks and even maybe transformers, I don't know, later on. But suffice it to say that we can treat that as this third component, this neural network, as a black box for the time being. Okay. Why? While we go a little deep into the first two, tokenization and embedding. To understand tokenization, you must actually experiment with them. There are so many online tokenizers available. Please go to those sites. I have given examples of a couple of sites, but there are so many. If you just search on the net for online tokenizers, there are a number of sites. So that will really give you an understanding of how tokenization works. So suffice it to say that tokenization is the process of breaking a text up into its components. The components may be, characters, words, phrases, and many other things. Each of these component is called a token. So that term token, you will find everywhere whenever you are talking about LLMs. Tokens need not be words. That is a fundamental understanding I want you to have. Tokens is not equal to words. In most cases, there are subwords. So if you go to that OpenAI site, tokenizer, they are using something called tick token, if I'm not mistaken. And you give a sentence there, you will find that it is not breaking up the sentence into just the words. For some words, it is breaking up into subwords. Okay. And finally, all these tokenizers have a database. This is a database, okay, where the tokens are mapped to some numbers. This is a pretty arbitrary. Each company, each software has its own tokenizer. If you remember the structure of that GGUF file, that file contains this database, okay, as to which token is mapped to which numbers. Okay. So that's how they deal with the tokens. So tokenization is the process by which the query that you are putting in, as also this huge amounts of text that are used during training, okay, they are broken up into small components. And these components are assigned numbers. These numbers don't mean anything. They have to be unique numbers for that particular software. Remember, there is no global tokenization database which all softwares, all companies follow. No, everybody has their own tokenizers. If you go to the site, Hugging Face site, for each model, you go to tokenizer.json, tokenizer config.json, if I'm not mistaken, you'll find all these details. Okay, so there is no global committee, okay, which will say, okay, the word Mr. is mapped to token ID number 18953. No, there is no such global committee, world token organization or anything like that. Okay, so every software, every model comes with its own tokenizer. Okay, and this mapping of tokens to numbers is in the model itself, like in the GGVF model I was showing. There is a section where this database is saved. Okay, it's not a very large database. Remember, you might think that there are so many words. Well, not every word is represented, but even subwords are there, as you can see on the right hand side. So strange things are there. Dog is there, work is there in caps, declare is there. Again, there are some words which doesn't seem meaningful. So nobody creates these tokenizers by hand. Again, some software programs are used. They are run on this huge body of text to generate these tokenizers. But for our understanding, it is enough to know that text is broken up into components, and these components are mapped to some numbers, so that internally, as you know, computers work on numbers, right? So somehow the query that you are putting to ChatGPT or Olama, whatever, and even the training data set, we'll talk about training a little later, they have to be somehow converted to these numbers. And tokenization is the basic process where the sentence, the stream of text, it can be a sentence, it could be a paragraph, okay, is broken up into meaningful elements called tokens. So that is this example of subwords, as I said. So some tokenizers are breaking up the text, explain large language models full stop into 5 tokens. Some other, so that was the human readable one. The tokenizer is now broken up the word explain into 2 tokens, X and plain. Okay. Now, why this happens? This is again a very involved subject. There are benefits of doing this. That is why people are doing it. Not arbitrarily looking at some words and saying this is a very large word, let us break it up. No, it doesn't work that way. If you are interested in the technical reasons why and how these words are broken up into subwords, please go read up on tokenizers. It's a fascinating subject, believe me. Okay. Many people don't even give any importance to tokenization, but that is a foundational thing. If tokenizer is wrong, then your entire thing is dead. Also remember, the tokenizer that is being used for breaking up the training corpora. We just saw a simple training corpora of 6 sentences. In a real life for ChatGPT, it will be 600 billion sentences. Okay. But again, each of these sentences have to go through a tokenizer. And that same tokenizer has to be used when you are putting in a query. So when you say explain large language models to ChatGPT, okay, the same tokenizer that was, otherwise there will be a mismatch, you understand. Because if the training model, while training, if the tokenizer used is different from the tokenizer used to break up your query, then this database that I'm showing on the right, this would not match, and the model would perform erratically. You will never know why the model is not performing. So this is a basic understanding that the tokenizer used to train the model has to be used to process your query also. Of course, if you're dealing with some software like ChatGPT and others, they're automatically doing it, obviously. Otherwise, and each model as we said, has this tokenizer as a part of the file. The GGUF file that I had mentioned, there was a section on there on the tokenizer, which just maintains this mapping from words or subwords to numbers. Okay, now that we have some basic understanding of tokenizers, that is mapping sentences, breaking up sentences to subwords and tokens, and then ultimately mapping them to some numbers. Let us move on to the next foundational concept of LLMs, that is embeddings. So this started with, the foundation of embedding is in the distributional hypothesis. So in 1957, as I said, these things are pretty old. Okay. So in 1957, this person, J.R. Furt, mentioned this. This has become like the Bible Love Foundation. That everybody mentions this sentence. You shall know a word by the company it keeps. You may have already heard about this phrase. Okay. So the basic idea is, how do you go to the meaning of a word? And this distributional hypothesis is a mechanistic way of understanding or trying to get a grip on the meaning of a word. Otherwise, meaning for us human beings, we have a different concept of meaning. But how would computers understand the meaning of his word? So the example given here is about two fictitious words. No such word exists, say GLORF, glorf, and the other word is wumble, WMBLE. So these are all fictitious words. Of course, the machine wouldn't know. Okay. So if the corpora, if you forgot about corpora, that's the training data set. Okay. That's the text, all that raw text, usually from the internet or from books, millions of books, millions of websites that are scraped and collected. So if that corpora has these sentences, for example, suppose it has the sentence in that corpora, she ate the glove for dinner. The glove was delicious and fresh. He cooked a glove slowly. I am hungry. Where's the glove? See, a computer has no idea that glove is a completely fictitious word, right? So what it concludes is that this word glove is surrounded by things like eating, cooking, delicious, hungry. So it's some kind of a food kind of a concept. That is how this whole thing works. You might have often wondered how these LLMs are understanding the meaning. There is no understanding. It's not a human being, right? We get trained on a physical world model. We actually see what rice is, what dal is, and other things. But a computer just trained on words, trained on a huge corpora. But after all, it's just words and sentences, right? So if this fictitious word is used in that corpora, so the machine will understand that this has something to do with food. So that is why Mr. Firth in 1957 said that you shall know a word by the company it keeps. That the words that are used often with that word. So the word ate is used with glorf, delicious is used with glorf. Similarly for the word mumble, this is again a fictitious word. There is no such word in the dictionary. Okay. An LLM never sees a dictionary. There is no dictionary. You might think that the Oxford Dictionary is some of it where the meaning of all these words are defined and from there it understands. It doesn't work that way. This humongous corpus that is available, and if it has sentences like this, she ran before her wumble, daily wumble keeps you fit. Obviously, the words that are surrounding this word, this fictitious word of wumble, are things like run, move, fit, tired. So it would associate the word wumble with something to do with exercise. So if somehow in your query you mention the word exercise, it may find the word wumble from the token. from its tokens. Okay, because during the training, that word wumble often came up with these concepts of running, being fit, and moving fast and tiredness and all that stuff. So the distributional hypothesis is the foundation of how the meaning of words are understood. I mean, the word understood itself is a little bit odd for a machine. We humans understand things. Machines are mechanically somehow they need to process this information. And this is the foundation that if the training corpora has words that are surrounded by some other words, so whenever the LLM, the language model, sees any word, it tries to find in the corpora. It was trained. I mean, it's not like a database lookup. Okay, it was trained to know that the other words that are near this word. So the word 8 is near the word glove. That is what it learns from this huge training corpora. Not 6 sentences, 6 billion sentences. Okay. So that's the point of this distributional hypothesis. Now, an embedding is like a mapping from a word to some space, some dimensional space. You forget about all this mathematics part basically, but you can see, that the model has learned this, that cats and dogs and lions and wolves are somehow near each other. Okay. Words like royalty, queen, king, prince, because in the training corpora, these words were near each other. I mean, the word jump is less likely to be in the training corpora in the same sentence with the word king. I mean, there might be a case where a king jumped from the window, but that sentence is a rare one. Okay. But whenever you see a mention of a king, it is highly likely that the same sentence had a mention of the word queen also. So the model learned that these are related. Okay, not similar though, it's related words. So this numbering mechanism that it comes up with, okay, it permits all these strange equations. Like if you have a embedding vector, some number, say, suppose, for king, man, woman, and then you actually perform arithmetic, vector arithmetic. Okay. So king minus man plus woman, you will get a vector which is near to the value of the vector for queen. Okay. So that is how these words are ultimately converted to numbers, basically. So that's the embedding scheme. Okay. In real life, I mean, you will find that each model, we mentioned that there is that section in a GGUF file also, which mentions how many dimensions are used in the embedding. Okay. So different models have different number of dimensions. I'm hoping that you understand what a vector is. So vector has a number of basically it's a collection of numbers. Okay, so there you will how many numbers a vector has again varies from model to model. But basically the concept is that these numbers are not arbitrarily assigned. It is again generated through learning. Going through this, humongous corpus of 6 billion sentences, say for example, the model learns that the word king and queen are somehow related. So when it generates those vectors, the value of the vector for queen is nearby to the value of the vector for king, say. Okay. A little away from prince, but quite different from the value of the vector for, say, jump. So that's how. So the exact process of how these vectors are generated is again a little bit more technical. Okay, if you are interested, you do a deep search on this. How word embedding, what algorithms are used to generate embeddings from training corpora. So if you do that exercise, you will get a little more understanding of how these exact numbers, whether the numbers are 4096 dimension vectors or even something smaller. Okay. And if, perhaps those of you are interested, you can write a Python program to generate these vectors from a, say, small corpus. Okay. So you take a corpus of, say, 100,000 sentences and you run this algorithm, and it will, the quality of the vectors that you generate will not be as good as of these large models that they have. Okay, but you can do things like this subtraction, and you can see if your corpus has these words like king, man, woman, and all these things. You'll also find, I mean, how close this one is basically. So the point is that this information about the context is compressed into a point in the space. I mean, this space that we are talking about, this space may be 4096 dimensional space, but each word is, this map to this space as a point there. And so if they are all vectors, you can compare, you can do vector arithmetic. And that's how you calculate whether one word is near another word or not. I wouldn't use the word, similar. I would use the word related. Okay. Many people confuse related with similarity. Okay. But these things are not, I mean, king is not similar to queen. King is related to queen. Obviously, cat and dogs are not equal, but they are related. They are all animals. So this relatedness is something which is automatically generated from the training corpora. It is not assigned by some committee or some software developer by hand. It is generated. And each model has its own way of generating these vectors. And there are so many embedding models available. You just search the internet for embedding models. Each will have a different number of dimensions. 4096 may be on the higher side. Sentence transformer, if I remember correctly, has 256 dimensions. That is a very popular embedding model. And this is the math. This is the math behind deciding whether two words are, I think the word similar is not the correct one. Related, I should have used. So related, cats and dogs, they are related. Yes, so the angle is semantic, angle is less, whereas cat with Paris or city, I mean, the angle is much larger. So the dot product, for those of you who are interested in math, I mean, the dot product will always give you a value between -1 to +1. So here +1 is set as identical, or very much, I would say, closely related. If the value is near 0, it is unrelated. And if the result of the dot product is -1, it's totally unrelated. I wouldn't use the word opposite, maybe totally unrelated. So this is the mathematics that is going on behind you. These huge corpuses tokenized and then converted to word embeddings or whatever embeddings is there. And then during the process, when the LLM needs to find nearby words, nearby tokens, it uses this kind of a similarity. I mean, people have heard about cosine similarity, but in most cases, in actual cases, dot products are used. So that's how so this brings us to more or less the end of this shallow level, I would say. Not very deep level, but at least shallow level understanding of how everything maps back to numbers. So you must have wondered, many of you, that how all this text stuff is mapped. So I'll just take a break for 2 minutes to just show you some example of this number and this vector thing. Just a minute here. Yeah, so this is a PDF file. Is it visible? Okay, so the PDF file is visible. Okay. So this is, for example, maybe you consider this as the something that was used for training a model, say. So this is some kind of a text file. So what is usually done is to extract the text from this file and then chunk it, okay, break it up into small portions of chunking, and then create embeddings for that. So I'll just show a couple of screens from our platform that we are developing, this MLOps, as well as platform that we are developing, where I have fed this. So I have fed this PDF document, and then it has been chunked. So that large, it's not very large, I guess a 9-page document. So the text has been extracted and then it has been broken up. So the first chunk, for example, it has this text, introduction, global scenario, etc., and it ends with the word by. The next chunk is, provisional data released by World Steel Association and all that stuff. So that's the second chunk. So eventually, each chunk is now converted using some model, some embedding model, to the embedding space. So I just wanted to show this screen to give you a real world example of how this embedding works. So we are using this 384 dimension embedding model. And so this is the full embedding vector for that chunk of text. So this is just a demo. This is a real life demo of how you can convert, say, a PDF file, you extract the text from it, and of course you don't create a dimension, a vector for the entire document. That would be too crude. Okay, so you break it up into small chunks, and then you vectorize it using some vector embedding model. Okay, some model. So this was just a 2-minute demonstration from our platform about how this embedding thing. So seeing is believing. You can actually see, how this. So this is being done for RAG, I would say. So whenever there is a query, so that query is also converted to a embedding vector of 384 dimensions, and then some sort of a similarity check is done using cosine similarity or dot similarity to find the chunks that are near the query chunk. So somebody may be asking about the status of the steel industry or what changes have happened in government policies in steel, okay, as they usually do. Okay. So this is what happens. The document is pre-processed, converted to text, broken up into chunks, and then embedded. So this embedding is kept in a database. For us, we are using the vector extension for Postgres. I mean, there are so many vector databases. Okay, you can use anything. And so you store this vector. So when a query comes, I should say vectors for each chunk. And then when a user puts in a query, you vectorize that query also using the same model, the same dimension basically. And then you try to find out that angle, which are the chunks that are similar to that. So multiple chunks would be coming as a result. So you take the top 5, the nearest top 5 chunks, and then you send it to an LLM. Of course, you convert it back to the text from the embedding vector. You have the text, right? So you send, suppose 1 and 3 are the most relevant ones based on this angle, this cosine or dot product or whatever it is. So you send all these chunks back to the LLM, and the LLM comes back with some kind of a nice answer. Okay. So that's how this vector embedding works. So that was just a 2-minute demo from how this. Okay, so instead of words, here we are doing a similarity check or relatedness check for chunks instead of words. But the basic concept is the same basically. So we now know about tokenization and then chunking and then some idea about this vector embeddings. So now we are technically qualified to understand how this whole world of text is converted to numbers and how they are compared, how various words and sentences and other things are compared to each other. Okay, so that's the basic machinery. Okay, so that's the basic machinery that is used in AI applications, in large language models and whatnot. So as I said, we are not going to go into the details of neural networks. So the same example I had earlier on with n-gram models. Okay, so if you think of the neural network as a black box, it's the same thing. Given the word models adapt through, we are expecting that the fourth word to be predicted is the word repeated. So internally, how it does, it's a different matter. But basically, it's the same thing. It's a language model which, when given some words, predicts the next one. That is all there is to it. Okay. I have also put up some, links here. Please do visit them to understand how all this, this, if you want to go inside this black box. We have some slides, but this is such an involved subject that it is going to take a lot of more time for this. Okay. So how text response is generated? The whole purpose of this and the next slide is to show you this, what is called the auto-regressive token generation. Some of you might be surprised to know that with all this sophistication, with humongous large servers and everything, okay, only one token is generated at a time. Okay, so that's the basic truth. So suppose you are putting in the query, okay, explain large language models, of course, and then ultimately the LLM generated the sentence. It started with this at least. Large language models are advanced, dot dot dot, and so many other things are there, right? So how is this happening? So when you say explain large language models, the model does not come up with a full sentence as the output. It's outputs one token at a time. So that's the whole point of this on the next slide. This slide is showing it as an abstraction that your input is tokenized. As you can see, it has broken up the word explain into two tokens. Then the tokens are converted to token IDs. Then the token IDs are converted to word embeddings. Then they are fed to the LLM, and there is some computation going on. Take this LLM as the black box here. Okay, this neural network transformer and all these things. So the black box ultimately outputs again numbers, token IDs. LLMs don't understand anything else. Then the software layer is there, the system layer is there. It sort of converts these token IDs into words, and then the words are converted as the response and sent back to the user. Okay. So that's how this whole thing works. We have mentioned two things like the encode method of the tokenizer. All tokenizers will have an encode method which will convert text to token IDs. And all tokenizers will also have a decode method, which is the opposite basically. Okay. Which will take the sequence of IDs generated by the LLM and convert it back to human readable words. Of course, again from that database. It's not inventing anything. There is no other high funda computation going on. Okay. All this thing is in the GGUF file itself, where the token IDs are mapped to words. So in the encoding process, you go from words to token IDs, and in the output, the decode method, you go from IDs to words. So that's how overall this thing works. Now, the point that I was mentioning is one token at a time. So this slide explains this auto-regressive text generation thing. The sentence is not generated as a whole. So the example here is those token IDs. Think for a moment that you don't see the word there basically, but these token IDs are input. Okay, and the model in the first iteration, it goes through iterations. In the first iteration, it outputs only one token ID. which corresponds to the word large. Then this token ID is concatenated with the input query. If you notice, the input query had 1, 2, 3, 4, 5, 6. 6 token IDs. So now it has come as the seventh. The output of the LLM, the first output token, is added at the end to this 6, so that the next input is a 7 token input. That is again fed to this black box LLM. Consider it as a black box, as a neural network, transformer, or whatever it is. And then finally, not finally, I mean at the end of iteration 2, it outputs the token 4128, which corresponds to the word language. Again, that token is added to the 7 token sequence as the 8th token. Then these 8 tokens are again in iteration 3 fed to this black box LLM, and the LLM comes back with the next token, which is 4119, which corresponds to the English word models. So this goes on and on, basically. And there are techniques to stop this. In earlier models, sometimes used to hallucinate and go on. You have to do a control C and stop it by hand. But now, of course, it has become much more sophisticated. I mean, there are settings of how many it would. Otherwise, the cost would go up. You could go on telling a story, but you want to stop it somewhere. If you ask an open-ended question like, what are large language models, it can go on and on. 5-page, 10-page output can be there. And of course, if you're using the free version, your token count will finish in the very first query itself. So for practical purposes, there are limits set by all the softwares. It is not in the model, mind you. It's in the software, in that system, where there are techniques to stop the generation after a certain amount of tokens are generated. Okay. You can set it. There are many software, the libraries and other things. You can set the maximum output token size, okay, of these Python libraries that you may be using. They'll have a parameter, max token. So it will stop generating after that. So this is the basic funda of how an LLM works. Numbers, from text we go to numbers, and then one token at a time is generated, basically. So that's, I don't know whether that is surprising to you or not. And when I first learned about it, it was pretty surprising. It almost sounds very dumb, doesn't it? We humans, I don't know whether humans are also working like this. We are so fluent, and all this stuff that we generate, whether it's text, whether it's how we speak, are we generating one token at a time in our brain, in the neural networks of our brain? I doubt it. I think we have a different mechanism of work. So, but a lot of people sort of compare when it comes to AI is becoming more intelligent, AI is becoming all powerful, but at the bottom of it, it's so simple and almost crude, one token at a time. So that is something that I want you to take back from this presentation. All this sophistication is around these LLMs, but at the very bottom of it, it's a very simple mechanism of generating the one token at a time. But it's in the quality of the tokens that it is generating. I think that is what is making the difference, rather than where it is one token at a time or multiple tokens and etc. etc. It's the quality. I mean, if you are asking, explain large language model, it is not coming up with something totally unrelated. So all these mechanisms that you have in that black box, that is ensuring that whatever token, it may come one token at a time, but it's very relevant to the query that you have put. That is why these things are becoming so useful. You are asking it to generate a letter, write an email, and of course, and it is coming up with what you are expecting it to do. That brings us to the final section, is how these models are trained. I will skip all these things because there is not enough time. You can go through this presentation later on. Yeah, we have only 15 minutes time left. So let us spend some time on trying to understand how these huge things are trained. So there are 3 main steps this, I kept on saying these humongous training corpuses, not that 6-sentence simple example that I had put up, 6 billion sentences. So as somebody mentioned in the chat also that it's trained on the internet and okay. So all these things are used, excuse me. Yeah, sorry about that. So this pre-training phase is where these humongous training data sets are fed toward this training application. It's a software, remember. No? There is no model here. We are creating that model. So these programs are running on multiple servers using hundreds and thousands of GPUs. And the output is the basic model. The output is the model weights, as we say. If you remember the structure of the GGUF file that I had shown earlier, that was the last segment in that file. So ultimately, so these foundation model weights is what we are generating. Of course, that doesn't go into the model file itself. That's the first phase. So we are generating the foundation model weights from the pre-training. Next is what is called alignment training. And this was the differentiator actually. This pre-training and all these things have been going on for some time, but the performance was never, useful. I mean, the next token that these models generated without alignment was not useful. It may be fun to watch the output of a pre-training. You give it a question and see what are the tokens it's generating as the next token and next token, like in that autodigressive loop. But that was not useful. It may be funny even. Okay. Totally irrelevant things it was generating. So when ChatGPT, first I think it was that company OpenAI, when they found that doing something like alignment training, we will get into that in a minute, the supervised fine tuning and then, reinforced learning with human feedback. And then the output became shockingly useful. So it was like a shock when this company first realized this. Okay. It seems like a game changer. So pre-training is where you feed it with large amounts of data by scraping the internet or giving these large data sets of PDF books and all that in multiple languages now, basically. But the output was not that useful. When these steps of alignment was done, then it appeared that you cannot live without LLMs now. Like for many people, it has become like the go-to tool, right from the morning to night. Okay. So how did this transition happen from something interesting but not useful to something damn useful so that we cannot live without it almost? That was because of that alignment tree. So that was the differentiator. Maybe it happened in 2021, I forget the date, but OpenAI found that this was the real differentiator when the output was becoming really useful for the queries that were being given to the model. So this is the supervised tuning, and finally is the after this reinforcement learning, there will be a session on reinforcement learning, I think for section 2, where you can see the details of that. So finally, you have this phase of so-called fine-tuning and in-context learning. Okay. So in prompt engineering, we do things like in-context learning. We give some examples in the prompt itself. So that's in-context learning. So the model uses that, converts that to embeddings and all that, and then uses that as the context. And fine-tuning is when you take the output of the model and fine-tune it for a particular application. You throw away some layers or you freeze some layers in that neural network and modify some parts of some layers in the network. So there are techniques for doing the fine-tuning. So that was for the downstream applications. But by itself, these foundation models, after the alignment training, they are useful for a wide variety of tasks. So let us just spend a little bit of time left on this 2 phases. So the pre-training is where, this humongous corpus is used to train, basically. So as we said, these tokens, the text is tokenized and then it is embedded. You already saw an example of how things are embedded. So here each token is then embedded, and finally you go through some mechanism of training that neural network or transformer network. Okay. So the main thing to note here is the size of this text, okay, and the number of tokens that are used, and the disk size. So just for comparison, Wikipedia is 0.001 terabytes, whereas this massive web corpus is 1.9 terabytes. So it consists of 604 millions of documents, 506 billion tokens. Okay. And then this final column is also interesting, the sampling proportion. A lot of these texts are garbage and not very useful. So they are sort of removed from the training input. Okay. So ultimately, you get some good quality training, hopefully, training data, that is. So that's the pre-training part. So you take a huge amount of text, you perform some cleaning, and this slide is showing that you end up with only 1 to 3% of the original token. So rest is all garbage and you have to throw it away. That is why you need more and more servers, you need more GPUs, more water, everything, just for training these models. And many of these companies are now trying to set up these data centers in India, basically, so that the environmental impact is in India rather than some other countries. So that's the background of what pre-training is. This is some just animation. Yeah. So the training model objectives is, excuse me. Yeah, so this was some animation which you can look at it as at your leisure, basically. Yeah. So I just thought I would mention these as you may sort of hear about this. Okay. That the training object, like causal language model, which predicts the next word. But then there are other models apart from this language models called mask language models, where you predict, you learn. The software is written so that the model tries to predict the masked words, not just the next word, but the masked word also. But mostly for the GPTs and other things like this large language model, it's the causal language models predict the next word, okay, rather than predicting the missing words. So the one on the left is the most common one today as far as LLMs are concerned. Now that we have some basic idea of what pre-training is, then what is supervised fine-tuning? So this is where you align, you create question-answer pairs. It's a very labor-intensive job. Okay. So that given a question, how do I change a tire? All the 4 answers that you see are plausible answers if you stop at pre-training. Remember, none of these answers are unrelated. So pre-training has achieved at least this. It is able to relate something in the training data set to the question. But is it useful? That is the point. The supervised fine-tuning is making the answer useful. So all these 4 answers are plausible because somewhere or the other, these tokens were there in the input data set. And the model, because of pre-training, thought any of these answers could come from the pre-training, okay, basically. But only the 4th answer is useful. So supervised fine-tuning is a mechanism where you train the model on a question and the appropriate answer. So there is no magic in this. Somebody has to painstakingly create this question answer pairs. If the prompt does not have a clue that can guide the interpretation, any of these answers is possible. I mean, there is no reason for the foundation model to prefer response number 4 over number 1. Okay. Because all this thing was there in the training data, but only number 4 is useful for the user. So for that, you need more than pre-training. So that is the supervised fine-tuning. So some simple examples of how annotation is done. You may have already heard the word annotation in your machine learning training. You have to annotate, okay, the training set. So if you're designing a classification training data set, you have to annotate or download already annotated data sets where the labels are annotated. So similarly here, you have the prompt and the response. So this is human generated. This is not, I mean, some other techniques may be used, maybe even some other LLMs are used to create these things. But for conceptual reasons, think of it as a human generated data set where there is a question and there is an answer. So the whole point is, okay, so that the model learns what is useful, not just what is related to the question. So that is how, for example, this example is showing two aspects. One is the helpfulness, the bottom one is related to safety. So the annotator has to create these examples and then feed it. There are techniques, there are software libraries, and so many other things which requires a huge amount of, maybe, I mean, the infrastructure required in this case is not as large as pre-training because these data sets are much, much smaller. The pre-training data sets are really huge. But nevertheless, without this alignment training, the model is not going to output useful. It may output something related, but the output is not going to, you're not going to like that. It would seem like it's a garbage, it's not useful. Nobody will use LLMs anymore without this supervised fine-tuning. And then you have this reinforcement learning with human feedback. This again is a more involved thing, but here you have a human being. Okay, so if the model is generating answers like you should end, the question was chatbot, what should I do with my life now that I'm 65 and retired from a long career in the circus? I mean, the chatbot really should not answer that you should end your life immediately. Would you like some suggestions for how to do that? So that the company would go bankrupt with the legal suit that would follow. So there is a human being sitting there which is looking at the responses generated by a LLM and then marking off manually that this is good, this is bad. And there are techniques, preference model, this, that, reward model. I mean, this is too complicated to get into this. Okay, and I'm not an expert in this anyway. So the bottom line is there is a human being, there is some mechanism which is now ranking the responses. Okay. So the previous one was giving examples of what is useful. And the second one is after SFT, supervised fine tuning, you ask a question to the model and you rank the various answers that it is generating. And based on that answers, the model learns that what is actually should be the output. So this alignment training is what has made this LLM world so useful and everybody is using it. Pre-training creates the basic foundation model, and on top of that, you perform supervised fine-tuning and reinforcement learning with human feedback. Okay, these steps are absolutely essential to make the output of the LLMs useful for you. So that is the learning from this, how LLMs are trained basically. So I think we have come to the end of this session. It's 9 p.m. Hopefully you have obtained some understanding of how the difference between the model and the system, and how this LLMs work, what is a tokenizer, how embeddings are actually mapping this text to numbers, okay, and then finally how these things are trained, the steps of pre-training which creates the basic model, and then how you make the model useful to this alignment training, such as supervised fine-tuning where you give it question answer pairs, okay, and in this reinforcement learning with human feedback where you rank the answers so that the model learns about which answer is the best one to provide. Yeah, all the PPTs and everything will be shared, I think. So that is not an issue. Okay. I mean, I couldn't go through all the slides, but so there was a question that there's a question. What is dimension here? I hope you understand the dimension is the, the number of components in the vector. A lot of people are asking for sharing the PPT, which we will do. What determines the dimensions of the vector? It varies. I mean, ideally, it should be as large as possible, but that is not the case. Okay, so many people have found that even smaller ones are useful. And then there are techniques of converting these large dimension vectors to smaller one, but still keeping them useful. So there are various techniques. RAG, yeah, we mentioned RAG a little bit. This how these documents are converted to chunks, and then from chunk is then embedded, and then so that's RAG. Yes, retrieval augment generation. I mean, embedding is a fundamental concept, whether you're talking about LLM or RAG or whatever. Right, right. So, Vidisha, can we stop the recording now? I think I have answered many of the questions. Thank you. Thank you for your feedback.
Diptendu sir, we can conclude the session, right?
Right, right, right. Yes, yes.
Okay, 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 okay.
So many
Thank
of
you,
them
sir.
have asked for the PPT. I think we have a policy of sharing the PPTs.
Yeah. I will share
Yeah.
with them. Yeah.
Okay.
Tomorrow
Sure.
with the class recording link. Along with that, I will share the class material as well.
Thank you. Goodbye. Good night.
Thank you, sir.